Alright, what's good, y'all? Ignore this mess. I was working on something else yesterday. But, yeah, so I was thinking, and I have this microcontroller book from last semester, and apparently it has its own, like, USB spec definition in here. So I'm gonna read through this and see how useful it is. Because it either could be more confusing or help me a lot, which I hope is the latter. So, let's go to projects. What am I looking for? Here we are, and then we're looking for to do. Right. So, what are we looking at? String descriptor. Oh, where is? Oh, there we go. It's taking a bit to load. Where is that one site I was at? There it is. This. So the endpoint descriptor. I want this over here. Oops. So for the endpoint descriptor, endpoint address. What number? I'm not sure what to do with that just yet. The attributes, I want this to be so for the different types, we can have control transfers to obtain basic information, use the USB device, and to read or set the status and address of the device. All USB devices must support control transfers. Oh, I see. It could be multiple. Endpoint descriptors are used to describe endpoints other than endpoint 0. Endpoint 0 is always assumed to be the control endpoint and is configured. Okay. All transfers are designed to provide relatively high bandwidth, but require the application to tolerate a long delay. The bus is busy. Printers, scanners, and mass storage devices use bulk transfers. It looks like I'll use interrupt. Okay, so it says here mice and keyboards use interrupt transfers. So we're going to want to use interrupt transfer, and must also do control transfer. So that means that this, if we're wanting to send the control, if we're on a control transfer, then this needs to be 0. Yeah. Okay. I see. So we don't need to worry about the special one where something was dependent on ISO, whatever. Interesting. So this is going to be interesting. Host will use this information returned from the descriptors to determine the bandwidth requirement of the bus. Sounds good. So at a low level, a transfer consists of multiple packets. There are 3 package formats: token packets, data packets. Okay, so for these descriptors, we can end descriptor. Oh, I see. Okay, so let's make, what is it, 2? No, we're looking for 3. So just do Okay, so USB is an acknowledgement thing, right? So we get a packet from the host, and then we send one back, and then they acknowledge that they received that package. If not, I assume we send it again. So, what did I name this? Just notes. Let's just say this is this desired descriptor values. And then we'll have the communication notes. Right. So we have three. Oops. There are three types. One. So we have token packets, which is sent by host. So you'll have sounds good. So we'll have the sync packet, which is 8 bits or 1 byte. And then we have the PID, which is another 8 bits. Oh, I see. So it did a 0, did a 1. Okay, I'll have to go back to this. Then you have the address, which is 7 bits. That's odd. Then you have the endpoint, which is 4 bits. And then I don't know what this one is. CRC5, which is another 5 bits. And then end of packet, which is 3 bits. And this is grabbed from page 5572. Okay. Oh, it explains what everything is. So we have, actually, let's do everything. And then we have the data packet, which is then sent by the device. So this is same thing. We should move this up. Right. So we have another sync, which is 8 bits. We have the PID, which is 8 bits. And then we have the data, which is 0 to, oh, hold on. Okay, Okay, here we are. Oh yeah, the big one. 1023 bits. That thing can be massive. And then the CRC. Oh, this one's different. 16. Oh, this just describes how many bits it is. And then the EOP, which is 3 bits. Right? And then we have the acknowledge packet, which is sent by host for in or by device for out. In. So my thing is, the transfer direction can either be in or out from the host perspective. An in token packet indicates that the host is requesting to read data from the target. Okay, cool. So, notes in and out are from the perspective of the host. Example, in is when the device is sending data to the host, right? So that's what we're going to be doing, because we don't care about information from the host. So the acknowledgement packet has a sync, which is 8 bits, and then a PID, which is 8 bits as well, and then an EOP, and a packet, I assume, which is 3 bits. So what I'm seeing is that the EOP is always the same, right? Yeah. And then we have the PID, which is also the same. The middle fields always change because we don't have CRFs on the acknowledgement packet. And then the end of packet is always the same. So I assume sync and EOP are how we know that data is either starting or ending. That's what I'm assuming. Oh, it tells me what everything does here. Okay. So sync is the sync byte is the first byte of the packet, right? So ensuring that the receiving clock is synchronized to the transmitting clock in the packet transfer. The value of the sync byte is OBs. Okay. For full speed, since the idle state is the J state, we're in sequence KJ. I see. Okay, so this ensures that the clock is synced with both host and device. Sync byte is always binary, should be 4, okay, 4, 1, 2, 3, and then that's right. So 1, 2, 3, 4, 5, 6, 7, yeah, because 8 bytes. Okay, cool. So for the PID, the PID byte identifies the type of packet being sent. Okay, so that makes sense. This is the type of packet being sent, and that's why we always have it. The lower 4 bits of the PID byte are the inverse of the upper 4. This inversion is used for error checking. Additionally, the least significant bits is sent out first. The lower 4 bits of the PID bytes are the inverse of the upper 4. The least significant bit is sent out first. So example will be 1, 2, 3, 4 is actually okay, but why? So the least significant bit is sent first. Right, because this is 1. Okay, so we only care about the upper part. And since the least significant is sent first. No, because that's most. Because that's this. No. That's this inverted. No, it's not either. I don't get that part. I'll have to come back to that. Address field. Device will use an address of 0 during the initial communication. So for the endpoints, interesting, uses 4 to identify 16 points within a USB device. The data field is just the data, yeah? I see. This is the data portion. The let's just say the field size just depends on the transfer speed and type that and then, oh wait, no, the CRC So this is what? Cyclic redundancy check field. We use the CRC to detect payload corruption arising in translation errors. Each token packet has a 5-bit CRC, okay? And each data packet has a 16-bit CRC. The basic idea of the CRC calculation involves 3 steps. First, let's say this, this is the section used for error detection or payload corruption. I don't know what the difference is, but so first, the data bits to be protected are treated as a binary number. Second, we divide the binary number by another predefined binary number. Finally, we select the remainder of the division as a CRC code. The receiver performs the same steps to compare the remainder calculated and the rest received. Typically, hardware circuits are used to calculate CRC for fast performance. We call contiguous sequence of erroneous data bits burst errors. An n-bit CRC can detect all single and double bit errors and any single burst error that is shorter than equal. Okay, so it says the data bits to be protected are treated as a binary number. After that, divide the binary number by another predefined binary number. Select the remainder of the division as the CRC code. So it's basically just a modulo operator. Oops. Then we have the this is twos. Consists of sicko for 2 time units of a bit. I don't know how it's going to work considering I'm not using all the wires. USB every 1 millisecond for full speed. The host does not expect any USB to turn in. Timestamps for USB devices to schedule data transfers, for example, the host packet. Oh, I see. A USB device can have multiple functions. For example, communication between the host and endpoints is known as a piper channel. An endpoint contains the endpoint number, transfer type. Properties of USB devices. Hierarchy of descriptors. So as example, yep. So we only have that. The device descriptor presents essential information. Oh, it actually gave the example of 1.1. And it was, what am I looking for? BCD, D, US, B, OX. I don't know if I need to put that or not. Okay. A device class code of 009. A diagnostic device and a vendor. Class code 0. Interface class determines the device class. Audio, HID. Okay. I don't need this. USB enumeration is the process of detecting and identifying a USB device. During USB enumeration, the host performs the following steps. Awesome, that's what I need. Because that's going to be step 1. Ooh. So, okay, so we detect whether their USB device is connected when there's change because the device pulls one of them off. Yep. So from our side is all I care about. I don't care about if it detects or not because I know it will. My USBs work. Oops. Determine the USB to feed as previously introduced, pulling up to the sample. Retrieve the device descriptor. Find which device is attached. Retrieve all configuration descriptors. Retrieve all interface descriptors. Okay. Request type, recipient, value, index, length. The host sends setup request whose standard format is given in 1952. Oh, here. The device responds to each setup request Shows an example procedure for receiving the data description. Note that the setup request is encapsulated into the data packet as its payload. Data packet direction after this request. It's device to host. Type is standard. Recipient is device. Get descriptor. Then what is the value for? W value. Oh, I assume that's which descriptor? First transaction, send the get. So the host will set get device descriptor will be OX06, right? Get device descriptor. Least significant first. Look, it's backwards. I see. 1101 is set up. Address endpoint. Oh, I see. You get this, and then the host will send, this is the sync packet, or the, what was it called? Yeah, this is the token packet, and then we send our data, which is this, and then this is the acknowledgement. Okay, I understand now. We already got this. It's just in boxing it with the rest of this. That's the link to this, I assume. So for our descriptor, we send, so for this device descriptor, they sent the link descriptor type, which was, I don't remember what 6 was, but whatever it was, 6, and then 1, the class is 0, yep, subclass is 0, protocol is 0. The packet size, you then use the length of this, and then you calculate this, send the end of packet. And then you do the same thing, you continue. We have the vendor, oh, they just omit the OX. Okay. So we have 1, 2, 3, 4, 5, 6, 7. Wait, no. 6, 7, 8, 9, 10, 11, 12, 15, 16, 17. It's not 20. Oh no, because you have multiples. 1, 2, 3, 4, 5. 7, 8, 9, 10, 11, 12, 13, 14. So why don't you put this here? So we have the length is descriptor type USB, which is 2 bytes, and then the class, yeah, get this. Oh, this is the retrieval, right? Okay, we'll come back to this. This is the one, right? Yep. After detecting that the USB is attached, the host waits 100 milliseconds to allow completion of the device plugging in, and issues a reset request. The reset request sets the device into the default state. Initially, the default address of the USB device is 0. Each USB device spawn. Okay, so it's a whole sequence of stuff. So you start by this detecting it, and then it requesting the descriptor, and then it now requests, oh no, it doesn't request anything, it sends us a reset, and we hold our address now. particular HID descriptor defines format. Yep. So these are for the reports. So I don't care about this right now. I wanted to get it detected. That is my first goal. The host sends setup request whose standard format is given. Flash responds to each request. Okay, I'm gonna take this book with me to. Actually, I don't want to touch these. Yeah. I'll take this with me to work and we'll figure this out. Because I can bring one of these with me. Let me make sure it's working first. Let's just use this. So if I put this in boot mode. Oh, I have one in here. I was using this one to test. So I'm almost certain that this one is working. So let's go to like here, and then F disk. Oh, there it is. This is ours. So our goal is going to be to change this and still make it show up. Size units. Yeah. But also, doesn't that mean I have to implement the boot mode? Oh, I didn't think about that. I'm not sure, we'll see. Because it could have two modes depending on if boot was held or not. Yeah, I didn't think about that, but we'll see. Okay, cool. I will work on that at work because I'm hungry now and I need to clean up.